Hey everyone, welcome to the third week of General Chemistry this final term. So let's begin. Have you ever wondered why we have compounds? Or have you ever wondered how the elements are held together to form such compounds? Well, the answer is that it is because of what we call chemical bonds. And generally, we have two main types of chemical bonds. We have the ionic and the covalent bond. And this is what we are going to discuss for this week. But before we proceed to ionic bonding, let us first try to unlock two important terms. We have here the octet rule and the Lewis dot structure. The Lewis dot structure, or also known as the Lewis electron dot structure or just Lewis structure, was developed by Gilbert Lewis. So in the Lewis dot structure, this is a structure that represents the valence electrons of an atom. So just a review, when we say valence electrons, these are the electrons found on the outermost shell of that atom. And a Lewis structure consists of the element symbol surrounded by one or more dots depending on the number of valence electrons that element has. So how are we going to determine the number of valence electron of each element in the periodic table? Here is the trend. The group number actually represents the number of valence electrons of each element. So for example, we have nitrogen, and nitrogen is located at group 5. So it means to say that nitrogen has 5 valence electrons. So we are going to draw 5 dots around the element's symbol. So we are going to draw 1, 2, 3, 4, and 5. Take note that in writing the dots, it should be that only 2 dots are placed in each of the 4 sides. So you may imagine the symbol as enclosed in a box, and then you are only allowed to draw 2 dots on each side. Okay, so you may also write the Lewis dot structure of nitrogen as having 2 on these sides and then 1 above, or you may also draw it as N, 2 on top, 2 at bottom, and 1 on this side. So it's all correct as long as you only put 2 dots on each side, and then just take note of the number of valence electrons you are going to draw for that specific atom. Now another example is fluorine. Fluorine is located at group 7, so that means to say fluorine has 7 valence electrons. So we are going to write the symbols, the element symbol, letter F, and then you distribute 7 dots around the symbol with 2 dots on each side. So we have 1, 2, 3, 4, 5, 6, and 7. So that's how easy to draw the Lewis dot structure of each element. And then we also have this what we call octet rule. So the octet rule, from the word octo, which means 8, states that when atoms of elements combine to form compounds, they tend to lose, gain, or share electrons to achieve the same electron arrangement as the noble gas nearest them in the periodic table. And take note, such octet is the most stable arrangement an atom can have. So as you can observe on the periodic table in here, we already have a group with 8 valence electrons. And this group is called the noble gases group. So the noble gases are already the most stable because they already reach the rule of 8 or the octet rule. They have high stability, therefore, they have a very little or no tendency to lose, gain, or share electrons. But it doesn't mean to say that they cannot bond with other elements. They could still bond and make compounds with the other elements. So let's begin now with ionic bonding. So I have here a creative illustration of what ionic bonding is. So as you can see, we have here two atoms. One is sharing, or one is offering its electron to the other atom. So it's like saying, take this and be mine. So that means to say, it is giving its electron to the other atom. So by this picture alone, you can say that ionic bonding is an electron transfer. So when there is transfer, meaning to say one is losing an electron and the other one is gaining an electron. Now the question is, which elements gain electrons and which elements tend to lose? So let's have a simple review on what ionization energy and electron affinity is, because these two terms were already included in the previous week. So let's just have a review this time. When we say ionization energy, this is the minimum amount of energy required to remove an electron. So the trend of ionization energy in the periodic table is this. As you go from left to right, there is an increasing ionization energy among the elements. And from bottom to top, there is also an increasing ionization energy. Remember that most metals are located on the left-hand side of the periodic table, and most of the nonmetals, or almost all, are located on the right-hand side of the periodic table. So this means to say that metals have lower ionization energy than the nonmetals. So if this is the trend, therefore, the metals tend to easily give up their electrons because they have low ionization energy. So metals tend to easily give up their electrons. Okay. The other term is electron affinity. This is a measure of the energy change that occurs when an atom gains an electron and forms a negative ion. So this time it's the gaining of an electron. So in the periodic table, the trend for electron affinity is from left to right. There is also an increasing tendency to accept electrons, and from bottom to top there is also an increasing electron affinity. So again, the left hand side are metals and the right hand side of the periodic table are the nonmetals. So that means to say that the nonmetals have a higher electron affinity than metals. So they have the greater tendency therefore to accept electrons. So what's the bottom line in here? The metals which tends to lose or to easily give up their electrons form cations. So when they lose an electron, that means to say they end up positively charged. And positively charged ions are called cations. And then for the nonmetals, which tend to accept more electrons or to gain more electrons, becomes negatively charged ions. And negatively charged ions are called anions. So going back to ionic bonding, therefore, this is a chemical bond formed between a metal, which is a cation, and a nonmetal or an anion. So if we have an element that is metal and a nonmetal, automatically they could form an ionic bond. Now, another determiner, aside from a metal plus a nonmetal, another determiner for an ionic bond to exist is the electronegativity difference of the two elements. As it says in here, the possibility that ionic bonding can exist between atoms of two elements can be predicted if the difference between the electronegativities of the elements is equal to or more than 1.7. So how are you going to know the electronegativities of the elements? They are found in your periodic table actually. You just have to look for it or you may just search it. So let's try this example to show how ionic bonds are formed. So number 1, show the formation of a compound between lithium and fluorine. So how do we know that lithium and fluorine could form an ionic bond? First, lithium is a metal and fluorine is a non-metal. Second one, let's try to see their electronegativity difference. So you just have to subtract. So the electronegativity of fluorine is 3.98 minus the electronegativity of lithium, which is 0.98. So if you are going to subtract that, the difference is 3. And since it is greater than 1.7, therefore, they could really make an ionic bond. So let's now try to draw the Lewis structure of these two to show their bond formation. So lithium belongs to group 1. So the Lewis dot structure of lithium is the element symbol plus 1 dot. Plus fluorine, which belongs to group 7, has 7 dots. So we have 1, 2, 3, 4, 5, 6, and 7. Now, we said a while back that lithium tends to lose their electrons while non-metals accept electrons. So in this situation, therefore, the lithium will give its electron to fluorine so that fluorine will fulfill stability, which is having 8 electrons in its valence shell. So if both already reach stability, then the ionic bond formation stops. So if you are going to assign now the charges of each element, so since lithium lost an electron, 1 electron, therefore the charge is positive 1 or simply positive. No need to write number 1. And since fluorine, which gained 1 electron or accepted 1 electron, meaning to say it ended up negatively charged. So its charge is negative 1 or simply negative. So this is the Lewis structure now of lithium and fluorine. So what is the chemical formula therefore of this one? The chemical formula is simply LiF, or this is also known as your lithium fluoride. Okay. Another example. Show the ionic bond formation of magnesium and chlorine and write its chemical formula. Again, magnesium here is the metal and chlorine is the non-metal. So let's try to get their electronegativity difference. The electronegativity of chlorine is 3.16 and the electronegativity of magnesium is 1.31. So 3.16 minus 1.31 is 1.85. So this is greater than 1.7. Therefore, magnesium and chlorine could make an ionic bond. So just like the previous example, we write each element's Lewis dot structure. Magnesium belongs to group 2, so it has 2 electrons, plus chlorine belongs to group 7. So we have 1, 2, 3, 4, 5, 6, 7. So again, magnesium, since it is a metal element, will lose its electrons. So 1 electron will be given to chlorine to make this 8. But if you are going to look at the magnesium, it still has 1 remaining electron. So what are we going to do to make magnesium stable also? So that means to say we need to add another chlorine so that it will have an element for it to give its remaining 1 electron. So another chlorine will be written or added. with 7 electrons, so that magnesium will transfer its electron to this one, making this also stable. So if we are going to assign charges of these elements, since magnesium lost 2 electrons, the charge therefore is positive 2. And since we used 2 chlorine atoms, and each chlorine atom received or gained 1 electron, the charge of each chlorine therefore is -1 or simply negative. So if you are going to write the chemical formula of this one, it's equal to MgCl2. This subscript represents that we use 2 chlorine atoms in the process. And this chemical formula is also known as your magnesium chloride. Another example is the ionic bond formation of potassium and sulfur, and then write its chemical formula. For potassium, potassium belongs to group 1, so we write it with 1 dot, plus sulfur, which belongs to group 6, so we have 6 dots around it, 1, 2, 3, 4, 5, and 6. Again, potassium here is the metal. It will give its electron to sulfur and non-metal. So it will transfer 1 electron in here. Now notice that if potassium will give its 1 electron to sulfur, it still doesn't meet the stable number of valence electrons because it will only have 7. So again, another potassium is needed for it to become stable, so that it will make sulfur with 8 electrons. So if we are going now to assign the charges of these elements, since we used 2 potassium atoms and each lost 1 electron, therefore the charge is +1 or simply positive. And then for sulfur, since it accepted 2 electrons, therefore the charge is 2 negative. Okay, so the final chemical formula for this one will be K2S, or your potassium sulfide. So this is now your chemical formula. So we are already done with ionic bonding. Next is covalent bonding. This covalent bonding here, as seen on the picture, we have here 2 atoms sharing their electrons on a table. Okay, so as I have mentioned, there is only a sharing of electrons, and as you can see, one of them does not give its electron to the other, nor neither of them accepted electrons. They are just simply sharing. So covalent bonding therefore is an electron share. But the question is, what elements are involved in the sharing of the valence electrons? So if ionic bonding a while ago involved a metal and a non-metal, for covalent bonding, it will exist between non-metal atoms only, which have small electronegativity difference. So the electronegativity difference of ionic bonding a while back is equal to 1.7 or more. But for covalent bonding, the electronegativity difference is below that 1.7. So let's try to see how covalent bond formation exists by answering this example. So you show the formation of the covalent bond for the F2 molecule or the difluoride. So just like what we did in ionic bonding, we need to write first 2 atoms of fluorine because it's a difluoride. So we have 2 fluorine. Okay, and fluorine is located at the 7th group, so we have 7 dots around it. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Now, how is the sharing in here? Take note that no atom is losing or no atom is gaining electrons. They are just sharing. So, if you are going to show the covalent bond formation is that, just have to simply write this. 2, 4, 6, 7, and 8. Now, take note that the dots in here are being shared by each fluorine's atom. So, no one is gaining, no one is losing. They are just sharing here. And this is where the covalent bond is located. Or you may just write it as F bonded with another F. So what does it mean? One line, take note that one line in covalent bond is equal to 2 electrons. So this line in here means that these two atoms of fluorine are sharing 2 electrons. So the question now is, or before I forget, the line in here is called a bond pair, and the dots around each are called the lone pairs. Okay, so the question now is, how many electrons are around each fluorine atom? So let us try to count. How many electrons does each fluorine atom have? So if we are going to divide this, let's start first with this fluorine. If you are going to count the electrons of this chlorine, we have 1, 2, 3, 4, 5, 6, and then this one equivalent to 2 dots is plus 2, that will be 8. And then the other fluorine here, let's also count. We have 2, 3, 4, 5, 6, 7, and 8. So the answer is they have both 8 electrons because they are sharing their electrons. And it's already correct because they already obeyed the octet rule. Another question, how many bond pairs does this formation have? So as you can see in here, we only have one straight line, meaning to say we only have one bond pair. How about how many lone pairs are made? Simply count. We have 1, 2, 3, 4, 5, and 6. So we have 6 lone pairs. So here is now a step-by-step process on how to write the Lewis structures of covalent compounds. So let's try to draw the Lewis structure of this example by following the steps. So write the Lewis structure for NCl3 or nitrogen trichloride. So the first step is to draw the skeleton structure of the molecule. So how are you going to know if what element is the central atom and which elements are to be attached? Now, if this is the chemical formula, generally when that element is only one or it doesn't have a subscript, this means that that element is the central atom, while the elements with subscripts will be the atoms attached to the central atom. Or another determiner to which element is the central atom is their electronegativity. So the least electronegative among the elements in the chemical formula will be the central atom. So for this NCl3, therefore, the skeleton structure is N with 3 attached chlorine around it. Okay. Next step is to count the valence electrons. Okay, so nitrogen is located at group 5 times 1 because it only has 1. And then chlorine is located at group 7 times 3. So we have 5, 21. So we have 26 valence electrons in all. So we must see 26 electrons in our drawing afterwards. And then step 3, you distribute the 26 electrons to the atoms such that they fulfill the octet rule. So what does it mean? From the skeleton structure, therefore, each element must follow the octet rule. Okay, so each must have 8 electrons. So we are now going to distribute the 26 electrons. So let's start first with the first chlorine. Okay, so chlorine in here has 2 electrons already because of this line. And it still needs 6 electrons to make it stable. So we are going to write now the remaining 6 as dots around it. So we have 2, 3, 4, 5, 6, 7, and 8. Also with the chlorine below, we have 2, 3, 4, 5, 6, 7, 8. And chlorine on this side, we have 2, 3, 4, 5, 6, 7, and 8. And lastly, for nitrogen, as the central atom, it has 2, 4, 6, 7, and 8. To finally check if this Lewis structure is correct, you count if we already put all the 26 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That means to say this Lewis structure is already correct. Another example, write the Lewis structure for OCS, or also known as your carbonyl sulfide. So again, we draw the skeleton structure. So which of these three, oxygen, carbon, and sulfur, will be the central atom? So as I have mentioned a while back, that the least electronegative element will be the central atom. So for this case, since carbon has the least electronegative value, it must be the central atom. So we have O, C, S. Next is to count the valence electrons. Oxygen is located at group 6. Carbon is group 4 element. And sulfur belongs to group 6. So add this, 6 plus 4 plus 6 is 16 electrons. So there must be 16 electrons in our structure afterwards. And then step 3, we distribute now the electrons using the skeleton structure. So we have O, C, S. Okay? Now let's try to complete first the carbon at the center. Now take note, guys, that in drawing Lewis structures, it's a matter of trial and error sometimes. So you may start to whatever element you want to complete its octet structure, or you may also start with the others. So it's up to you. So it's a matter of trial and error. For this time, I'm going to start with carbon. So carbon in here has 2, 4 electrons. So it needs 4 more to make it 8. So I'll draw another 2 lines. So for carbon, it has 2, 4, 6, 8 already. So carbon is already stable. Now next is oxygen in here. As you can see, it has 2, 4 because they are sharing, it's sharing with carbon. 2, 4, 5, 6, 7, 8. So oxygen is already stable. For sulfur, it has 2, 4, 5, 6, 7, and 8. Sulfur is already stable. Now let's check if we already put all 16 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16. Therefore, this is already correct. Now, you might be wondering why we could not make triple bonds or just a single bond between each element. For example, why can we not write it as like this? 2, 4, 6, 8. 2, 4, 6, 8. Okay. Why can't we write it just like this? What makes this Lewis structure wrong? Now, always remember that, as we have mentioned, the group number represents the valence electrons, right? And the group number also represents the number of bonds that that element could make. Okay, so the group number represents two things, the valence electron and the number of bonds. So what makes this wrong is that first, carbon here only has 6 electrons, although both of the attached elements obeyed the octet rule. And one thing more, since carbon here has 6 electrons, it also only has 3 bonds. So we have 1, 2, and 3. So here's how you are going to count the number of bonds. One line corresponds to one bond, one dot corresponds to one bond. So if you are going to count the number of bonds of carbon in here, it only has 3. These 3 lines, 1, 2, 3. And since carbon is located at group 4, it has 4 valence electrons, meaning it also could make 4 number of bonds. But on this structure, it only has 3. So this makes a wrong structure. One thing more, oxygen in here is correct because it has 8 electrons, 2, 4, 5, 6, 7, and 8. And then it also has 6 number of bonds for oxygen. So it's correct in here. Where is the bonds for oxygen in here? Where are the bonds? So it has 1, 2, 3, 4, 5, 6 bonds. So oxygen in here is correct. Carbon here is wrong. Another one is sulfur in here. Sulfur belongs to group 6. So it means to say it must have 6 number of bonds. So what makes this wrong is that it has 1, 2, 3, 4, 5, 6, 7 number of bonds. So this is a wrong Lewis structure. This must be the correct one. So know when to make double or triple bonds by basing it to the number of bonds that each element could only make. Another example is the Lewis structure for C2H4. So the first thing to do is to write the skeleton structure. Carbon is less electronegative than hydrogen. Therefore, carbon will be the inner atom than the hydrogen. So we write 2 atoms of carbon with 4 hydrogen. Next is to count the valence electrons. So we have carbon is located at group 4 times 2 and hydrogen belongs to group 1 times 4. So this is 8. 4. 8 plus 4, we have 12 electrons. Third is to distribute the 12 electrons to the atoms such that they fulfill the octet rule. So for carbon, and then hydrogen. Okay, so let's start with these 2 carbon atoms at the center. So the first carbon, as you can see, has 2, 4, 6 carbons. Also with the other carbon, 2, 4, 6. So each of the carbon needs 2 electrons more to make them 8. So we'll draw a line in here. Okay, so let's check for carbon in here, 2, 4, 6, 8. Another for this carbon, 2, 4, 6, and 8. So each of the carbon is already stable. Now let's check if they met the number of bonds. Okay, which is 4 for carbon. So let's check for carbon here. We have 1, 2, 3, 4 bonds. And other carbon, 1, 2, 3, and 4 also. So it's already correct. Now let's check if we already put all the 12 electrons. So we have 2, 4, 6, 8, 10, 12. So that means to say this Lewis structure is already correct. Now you might be wondering why we did not complete the octet rule for hydrogen. Take note, hydrogen is an exception to the octet rule. Hydrogen is an exception to the octet. Why? Because hydrogen could only hold 2 electrons. That's the maximum for hydrogen. It doesn't need to completely obey the octet rule because clearly it could only hold or carry 2 electrons on its shell. Last example, write the Lewis structure for NH4 positive. Now notice for this example, it has a charge. Now take note, as we have mentioned a while ago in ionic bonding, an element or an atom becomes positively charged if it lost an electron or if it loses an electron, right? So how are you going now? So let's draw first the skeleton structure. So we have N with 4 hydrogen atoms. So how are we going now to compute the valence electrons of this charged polyatomic ion? So nitrogen belongs to group 5, hydrogen belongs to group 1 times 4. So we have 5, 4, 9 electrons. Now, the charge in here suggests, just like what I've mentioned, that this molecule loses an electron. So, if it lost an electron, therefore, we need to subtract 1 from the total in here. So, it's 9 minus 1 means to say that the whole NH4 positive has 8 valence electrons. Okay, so that's how you are going to compute for the valence electron if it is a charged molecule. So, what if it's NH4 2 negative? So, since the charge is 2 negative, it's a negatively charged ion. That means to say it gained an electron. So, if originally the valence electrons total is 9, you just have to simply add 2. So again, if the charge is negative, you add. If the charge is positive, you subtract. Next, we distribute the 8 electrons to the skeletal structure, the skeleton structure. So we have N, H, 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 and H. So let's try to take first nitrogen, check if it already has 8 electrons for it to become stable. So nitrogen as the central atom has 2, 4, 6, 8 electrons already. So this structure is already correct because the total is 8 electrons. We already put it in the structure. And as I have mentioned a while back, that hydrogen only carries a maximum of 2 electrons. So this is now the structure of NH4 positive. So here are some of the 2 important exceptions to the octet rule, aside from the hydrogen that I have mentioned. First is the incomplete octet. So let's take BeH2 as an example to explain incomplete octet. So Be or beryllium belongs to group 2 and hydrogen belongs to group 1 times 2. We have 2, 2, the total is 4 electrons. So if we are going to write the Lewis structure of this one, Be, H, and then another H. So if you can see in here, beryllium doesn't need to meet the octet rule. What's the reason? As I have mentioned a while back, that the group number represents the number of bonds that element could make. So since beryllium belongs to group 2, and in this structure, it already met the number of bonds, which is 2, then therefore, this is already correct. So beryllium doesn't need to obey the octet rule because of this exception. It's an incomplete octet, also with the hydrogen. Another exception is the complete opposite of incomplete octet is the expanded octet. So this is the opposite. If the central atom, take note, belongs to period 3 and beyond in the periodic table, or the period 3, 4, 5, 6, and 7, it could hold more than 8 electrons. Okay, so let's take SF6 as an example. sulfur belongs to group 6 and fluorine belongs to group 7 times 6. So this is 6. This is 42. So 42 plus 6, 48 electrons all in all. So the expanded octet is just like this. So we have S, 1, 2, 3, 4, 5, and 6. So we complete each fluorine with 8 electrons. 1, 2, 3, 4, 5, 6. Okay, as you can observe on this example, each fluorine atom obeys the octet rule. Each has 8 electrons. But the sulfur, as the central atom, exceeded 8 electrons. This structure is still correct because, as mentioned in this exception, that if the element belongs to period 3, 4, 5, 6, or 7, it could hold more than 8 electrons. And sulfur belongs to group 6, therefore, it could hold more than 8 electrons if it becomes the central atom. And one thing more why this is valid, because sulfur belongs to group 6, therefore it could make 6 bonds also. So we have 1, 2, 3, 4, 5, and 6. So that's all for this week. Thank you for watching. I hope you saw the difference between ionic and covalent bonding. If you have questions, please feel free to ask it through the discussion board in the LMS or through our group chat. And I would like to end this lecture with this quotation. Sometimes it takes losing everything you thought you needed to gain something you ever wanted. Good day, everyone.